All right. In this video, we're going to talk about random numbers. So to start, let's look at several different ways that we can generate random numbers. The first way we introduce is not to use any technology. We just use the random number table that people has already generated before. So, for example, here this is a list of um, some random digits. And you can find this from a textbook, this table 7.4. You can actually also find a bigger table of, I believe it's 1,000 random digits in the appendix of your textbook. So what this table does is it gives you 100 digits generated randomly. So like first one is 1 and then 5, 5, 4, 4, 8, 0, 7, 1, 2, etc. So you might wonder, hey, I don't see a pattern here. Well, that's right. That's right. Because they're supposed to be random. If you don't see a pattern, that's normal. That's what it should be. Now, we're going to learn how to use this table to create, let's say, 5 elements and without replacement. So here, let's say we have a list of 75 items. You can think about it, 75 people. You want to draw 5. You can do a lucky draw and get 5 winners. So what you do is you grab a table like this and you start from the beginning and you just read the digits and 2 digits at a time because we have 75 of them. That's a 2-digit number. So we read the first one as 15. So number 15 is the first lucky one. And then the next one is 54 and right here, and then 48. So the next one is 48. And then the next one is 07. So it's the number 7 and then number 12. So this is how we get 5 random numbers from there. I do want to make a few comments about this. First of all, what if the next number, what if the number is beyond the boundary? Like, for example, if you do the next one, you get 97. The solution is simple. We simply skip it and move on. So we just skip it. There's no such a person with the number 97. We'll move on. And then the next one is 74, and that's a valid number. And then second is, what if the number repeats? Like here, you got a 22, you got a 15 again. Well, because in this specific setting, we are doing this without replacement, and therefore we don't worry about it. And we simply skip it and move on. We just treat it the same way as we did with the number out of boundary. We just can't do 15 anymore. However, if the question allows replacement, then you should include this 15. 15 maybe it's just double lucky and you just choose the same person the second time. All right, and there is a second method, and that's called ordering. And I don't want to go too much into the details of that because it's first of all it's not important, and secondly, I believe it's unnecessarily complicated. We just don't need to worry about that. But for those of you who are interested, let me just quickly mention the idea. The idea is we're going to assign each item with a random number. This is actually generated at the from the table 8.7, 8-7 in Appendix 3 at the back of the book. So basically, you're going to give each item number a random number. And then before you, of course, before you do that, you predetermine a rule. For example, whichever number has the smallest random number will be the lucky one. So for example, if you want to choose one random item, that would be number 2 because number 2 has the smallest random number. And what if you want to choose 2 smallest one, then that's 2 and 60. I mean, actually, sorry, the smallest one is actually 50. The second smallest one is 2, the third smallest one is 60, and so on. And what if there is a tie? Well, if there's a tie, we just look at the next digits. And we look at what is the next digits. That's not given here, but you can find it on the table. Again, this method is not as important and it will not be required for this course. Now we're going to look at how to do these things in R. So here, one thing you can do is to use this command. This time I'll run R online, and you can use the sample and from 1 to 10, and the 6 elements replace equals true. So this basically tells the R that we want the 6 random numbers. The smallest possibility being 10, 1, the largest one means the smallest one being 1, the largest one being 10. We want 6 of them, we allow replacement. So we see here, the result is 3, 2, 3, 5, 4, 3. So you see here, 3 that's repeated 3 times. That's normal because we allow replacement. If you just simply run the same command one more time, you get a different result. And if you do it again, you get a different result because that's what random means. Those results are completely random. And what if you change this replacement from true to false? Well, the difference it makes is now instead of allowing replacement, we don't do replacement anymore. So, or in other words, those numbers are not allowed to repeat. So you see here, look at these 6 numbers, they don't have repetitions. And you can do it again and you get a different 6 unique numbers from 1 to 10. And also let me mention that what if this parameter is just missing? Well, if it's just missing, by default, we treat the replacement as false. Or in other words, if you just run it, you don't see a repetition. So you can either run it just without this addition parameter, or say the replacement equals false. That means no replacement. But if it says true, then we allow replacement. So those are the few comments that might be useful. Notice that last one will give an error. And so because think about that, if you're trying to do 14 numbers from the list of only 10 numbers, you can't do it because there's only 10 of them. You can't do 14 numbers unless you allow replacement. So you see here, cannot take the sample larger than the population when the replacement equals false. However, if you do the replacement equals true, and then that's okay because every time you draw a number, you just put it back. Every time you draw a number, you put it back, and so on. So this one will be no problem. All right, so now let's take a look at the next real life practical problem. Suppose we want to study the elders from the Conservative Church of Christ, and we'd like to discuss, hey, how many elders are connected to Florida College in the sense that they either worked here or studied here before? So, well, in order to understand this problem, ideally, if you can have a consensus, if you can just study every elder of all the conservative congregations, that can be done, but this becomes impractical. This is not easy to do it. So on the other hand, an easier way we can do it is to take a small size sample, such as 100. If we do a small size sample, and then here, from a practical point of view, we don't really know the percentage. So here, we would guess, this is just a guess. We guess that P is, let's say, roughly 5%. This is on a guess. We don't know for sure. And now here, suppose we guess it's 5%, and then we can do the standard deviation. So sigma equals the square root of the variance, which is P times 1 minus P over N. And using our guess that P equals 0.05, that's a guess, we get sigma is about 0.02. So this is the standard deviation, sigma equals 0.02. And how is this useful? Well, the reality is, in many of the problems, about 95% of the time, the sample mean falls within plus or minus 2 standard deviations of the true mean about 95% of the time. So, or in other words, with a sample of size 100, we have 95% confidence that the true value is within 2 standard deviations away from what we find from the sample. Let's say you have 7 out of 100 of people you surveyed are related to FC. So this is 7 out of 100. And so the observed probability is, or the percentage is 7%. So the conclusion is that you have 95% confidence that the true value P will be within 2 standard deviation. 2 standard deviation would be 2 times 0.02. That is 4%. So 0.07 plus 0.04 and also 0.07 minus 0.04. So this is about 0.03 to about 0.11. Or in other words, what I'm saying is that if you just take a sample of 100 random elders and you found that 7 of them are related to FC, and then you are 95% sure that the real percentage is somewhere between 3 and 11%. Could you be wrong? Yes, for sure, but you are 95% confident that your result is correct. All right, so, well, the next slide is not particularly important, but what I'm saying is that for larger surveys, if you want to sample more people, like tens of thousands of people, then it becomes very impractical to do it by yourself. you need a larger sample size. You probably need to hire some professionals to do so. And of course, the larger the sample size is, and if you look at this formula, the larger this n is, the smaller the standard deviation is, which tells you that your result will likely be more accurate. You can have a better understanding of the true probability. But the problem, of course, with larger sample is that you have to pay them more. The more people you ask them to sample, the more money you're going to pay. So there you have to find a balance. All right, finally, let's talk a little bit about simulations. Random numbers can be used to simulate some probability experiments. And let's say for our purpose, we'll just generate one random number. In this case, doesn't matter if you do replacement or not, from 0 to 9. You can do 1 to 10, doesn't really matter. Let's say from 0 to 9. And now what we can do with this random number is we can use this to simulate a lot of real life scenarios, such as tossing a coin. You have to make a decision. Let's say I determine that even number means the head, odd number means the tail. It could be the other way around, doesn't matter, but you have to make a rule. Even number means the head, odd number means the tail. So every time you flip a coin, you can just run this command once. That gives you a random number. This is 2. So you mean, hey, we got a head. You can do it one more time, and then you get a 1. That's the tail. And do it one more time, you got a 3. That's a tail, and so on. You can also do a throwing of a die. And throwing a die, you can get any result between 1 and 6. You can either run this command and just discard any values beyond 6. For example, if you get a 7, just do it one more time, because 7 is not a valid output when you throw a die. But now the next time you do it, you get 0. That's not valid also. But then the next one you do it, you get 2. That's a result. Or even easier way to do it is simply changes this from 0, 1 to 6. And then you can run it once. And this will guarantee that your result is between 0 and between 1 and 6. And of course, the next time if you need to play some board games, if that board game involves flipping a coin or throwing a die, if you don't have it, you know you have R. You can use R for that very purpose. You can even simulate things with different probabilities. Let's say we have A, B, C have different probabilities. A has the probability of 3%, and B has 22%, and C has 75%. So you can give A 3 numbers such as 0, 0, 0, 1, and 0, 2. And B will be 0, 3, 0, 4, all the way up to you have to count 22 of them. Of course, you don't really need to do real counting. You can just do some calculation. 24. And the reason why this is 22, because you use 24 minus 3 and then plus another 1 will give you 22. And the C will be 25 all the way to 99. So, and then every time you generate a number, so here you can adjust your R command from 0 to 99. And every time you generate a number, that will give you a scenario, either A, B, or C, depends on what number is generated. So the first one gives you 22. So that's actually a B. And then let's just run a few more times. Let's just run one more time. You get a number 23. That's still a B. And let's do one more time. And now this time you get a 83, that's a C, and so on. So you can use this to do experiment with ABC with different probabilities. So you can see this random numbers are really fun and has a lot of uses in real life. And I hope everyone enjoys doing this. Thank you very much. I will see you in the next chapter.